Hello again, everyone, and welcome to part 3 of our lecture on Chapter 10, Analyzing Quantitative Data. I know Chapter 10 is a bit long, so I wanted to break up this lecture into quite a few different portions just so it's a little bit easier to digest. So I appreciate you sticking with me and promise this is the last part of our lecture on Chapter 10. So, in parts 1 and 2 of chapter 10, we really were talking about the different ways that we can sort of set the groundwork in understanding quantitative analysis. So, in part 1, we talked about univariate analysis as well as how we can use that to establish measures of central tendency. And then that led into chapter 2, where we talked about measures of variability and dispersion and graphic representations of our data. So, in chapter 3 here, what we're going to do is we're going to go into more detail on a little bit more advanced analyses that you can use in quantitative studies. And sort of the broad category that we use to understand these more advanced analyses is bivariate analysis. And bivariate analysis is used to investigate the relationship between two variables. Particularly, we use bivariate analysis to understand whether the changes that we see in one variable are reflected by changes in another variable of interest to us. And there are multiple measures of bivariate analysis that are common in psychology. The first of those is correlation, which is used to determine the extent to which two quantitative variables are or approximate a linear relationship to one another. But we also have regression, which is used to identify the line that best describes the relationship that we've established through correlation. So we're going to go into a little bit more detail on what all of these mean, but basically, bivariate analysis is our attempt in statistics to say, I want to understand the relationship or how two variables influence one another. Correlation can be used for that, but we can also use regression to best understand how variables are related to one another. So let's go into a little bit more information by starting with a really common component of bivariate analysis, which is the linear model. A linear relationship between variables is a perfect relationship between two variables that, when we graph it out, resembles a straight line on an XY graph. So when we say that we have a linear model, or a linear relationship, we would say that there's a perfect relationship between these variables and that 1 unit increase in one leads to a 1 unit increase in the other, and it creates this perfectly straight line on a distribution. In a linear relationship, the changes in units of one variable are reflected in a specific interval change in the other variable. And that change doesn't vary depending on the size. So it is always the same no matter where we are in the distribution. That change in one variable will always lead to the same amount change in the second variable. But honestly, in social sciences, linear models are extremely rare in our research findings because most of the variables that are collected from participants will have variability in the answers. There is very rarely, if ever, a perfect linear model in psychological research, but we still talk about it because it provides a base for why we do other analyses. So, one of the other analyses that is common is correlation. So, correlation is used to look at again the relationship between variables, how they are related to one another. And when all data in a data set is cleaned and entered into a software program, a lot of scientists and psychologists will typically run an analysis using what's called a Pearson correlation coefficient, which is also sometimes just called R because that's the actual coefficient that we use. And we use the Pearson correlation coefficient as an index that determines the level of correlation between two variables. So a Pearson correlation coefficient is really helpful as like a first step in seeing how variables are related to one another. And we use them a lot because there are these standard pieces of a Pearson correlation coefficient. Namely, a Pearson correlation coefficient R can range in value from -1 to 1, indicating the level of linearity between variables. So, in other words, the closer our R coefficient is to -1 or 1, the more closely that relationship resembles a linear relationship. So a 1 or a -1 would represent a perfect linear model. So the closer you get to those values, the closer your data is getting towards that linear model. But the closer our coefficient R is to 0, the less likely it is that the two variables of interest in our study are correlated with one another. There's no relationship between them actually. A score of 0 on a Pearson correlation coefficient represents zero relationship between those two variables. Those two variables do not influence one another in any predictable way. So correlations of 1 and -1 are perfect positive and negative relationships, respectively, while a correlation coefficient of 0 indicates that there is no relationship between our variables. So really, when we're talking about correlations, we use these as approximates of our of understanding how variables are related to one another, but also as a first step in understanding how variables just even go together. So, Pearson correlation coefficient is the most common correlation model that's used, but there are other correlations that are of interest as well. And one of those is the Spearman rank coefficient, which is sometimes just called the row correlation coefficient, which is a correlation between two variables that is actually in equal value to the Pearson correlation. But the difference with the Spearman correlation is that it is between the rank values of two variables. So we specifically use the Spearman rank correlation coefficient or the row correlation coefficient when we're working with ordinal variables. Pearson correlation coefficients can be used with interval and ratio variables. And we also have a measure correlation that can be used with ordinal data. Or sorry, not with ordinal, with our base data. So looking purely at categorical data and or nominal data, I apologize. And that is what we call the phi coefficient, or sometimes it's called a mean square contingency coefficient. And our phi coefficient is a measure of the association between two binary variables. So you're working with nominal variables that only have two levels, and you're really comparing them. So you have like what's called a 2 by 2 model, and you're just looking at how those variables are in relation to one another in a very simple format, because your variables are very simple. Nominal variables are very simple variables, so you have to use a simple analysis for understanding the relationships between them. So I briefly mentioned that with correlations, you're looking at the relationships of variables. And even with the Spearman and the phi coefficient, we're still looking at those relationships. And one of the ways that we look at how they're displayed is through a correlation with a linear regression. So as you can see here, we have what's called a positive correlation, which occurs when an increase in one variable leads to an increase in another variable. This is a positive correlation. As one variable increases, the other increases. But you can also have a negative correlation, which represents as one variable increases in size, the other decreases in size. And it's possible to have no correlation in your variables, which might look something like this. There's no meaningful way these variables are sort of graphed in relation to one another because they don't influence one another. They're not related. So, one of the key things to keep in mind with correlation is the fact that two variables are strongly correlated with one another does not mean that one variable causes changes in the other variable. In fact, you probably heard this in undergrad, and I'm going to repeat it here. Correlation does not equal causation. So, causation says we can say that a change in one variable will cause a change in another variable. And the only way that we can establish causation is through an experiment where we can control the timing display of variables. And in correlations, we don't have that control. We're really just looking at how these variables are related to one another. And saying that a variable has a high correlation does not equal causation on that variable. We cannot say which one came before the other because the inverse could be true. And sometimes there could be something else that's coming into play, and we call this a spurious relationship. So, a spurious relationship happens when the correlation between two variables is affected by a third variable that interferes with the relationship that we're studying. And if we take a correlation and assume causation, we could be discounting the influence of this third variable, the spurious relationship in understanding our data. So keep in mind that if you are doing a correlation, it does not equal causation, even if you have a high correlation coefficient. So, the other common example that we use of bivariate analysis is regression, which is sometimes also referred to as our best fitting line. So, regression represents the closest possible linear relationship between two variables. And regression is used to predict future behaviors of our variables as much as to explain current behaviors. So a lot of times we use a regression or a best fitting line to describe what is going on in our data right now and how might we suspect it to continue should our variable increase dramatically, like times 3 of its current size. What might we predict that relationship to be based on the relationship of those variables now? So, the way that a regression line works is it establishes the best fitting line of the relationship between variables while also telling us the direction of a relationship. And also, sometimes this is called a simple linear regression. So it's looking at how strongly are these variables related to one another and in what direction are they related. So when we're working with a linear regression, a lot of times we start with a scatter plot. So a scatter plot is a visual depiction of a bivariate relationship. So we oftentimes use the scatter plot as a starting point for establishing a linear regression or a linear model. And graphically, scatter plots are dots on a graph that represent a relationship between two quantitative variables, a dependent variable and an independent variable. So once you're in the graph, each single dot represents one case in our study, one singular answer on that independent variable in relation to the dependent variable. And the dependent variable is always displayed on the vertical y-axis, and the independent variable is always displayed on the horizontal or the x-axis. And we use the scatter plot to sort of just graphically display our data so that we can then establish a regression or a best fitting line. So here's a couple of examples of what scatter plots can look like. So this first one, we can see a strong positive linear relationship between variables. Our data points are closely together. They are going in a positive direction. So as one variable increases, the other increases. And it's pretty strong because those variables are close together. Those data points are close together. But not all studies look like that, and a scatter plot can help us see why or how they are in relation to one another. So, for example, we might see a little bit wider of a spread in our data, but still a general trend in a downward fashion. So, we would say that this is still a linear model and that there's one straight line, but it's definitely going down. So, it's a negative relationship and it's moderate because our scores are a little bit more spread out. We can also see from a graphic scatter plot that there's no relationship between variables sometimes. Our points have no relation, they're just sort of all over the place. But we can also see that sometimes a scatter plot indicates that we need to use a different measure of how our variables are in relation to one another because the relationship is not linear. It's not a straight line. And here's an example of what that looks like, where we see this arch in our relationship. So these variables are definitely related to one another, but not in a standard linear model. So scatter plot can really open the door for understanding how our variables are in relation to one another. So correlation and regression are really helpful in understanding how variables are in relation to one another. But sometimes we want to run analyses for testing the differences in variables. So there are many different ways for testing differences in variables, and I put all of them up at once because I want you to see how they are in relation to one another, but also how similar they are to one another. So the first of these is what we call the chi-squared, and the chi-squared is used for nominal categorical variables. And the chi-squared is a statistical test that is applied to sets of categorical data to evaluate how likely it is that any observed differences between those two data sets is by chance. So we use a chi-square analysis specifically for nominal categorical data to say, in any differences in these variables, how likely is it that these differences are due to chance? We also have a significance test, and a significance test is used with ordinal data or rank data, and above it can be used with interval and ratio data, yes, I apologize. It can also be used, okay. So the way that it works is that each of these analyses can be used with more advanced types of data. So a chi-square analysis can be used with any type of data, but at the base, is the only one that can be used with categorical data. But the more advanced your analysis gets, it cannot go in reverse. So if you have an analysis that can only be used with interval or ratio data, it can only be used with that. It cannot go in reverse. But something can always go further forward because it's more simplistic. So, for example, a significance test at its base can be used with ordinal data, but it can also be used with other types of data that are a little bit more simple because it's a more simple or more complex data because it's a simple analysis. So a significance test is used to help quantify whether a result in an analysis establishing differences between groups is likely due to chance or some factor of interest. So when we say that a finding is significant, it simply means that you can feel confident that a difference in a variable is real and not that you just got lucky or unlucky in choosing a sample that had that difference. We can also use additional analyses that are used with interval and ratio data. And one of those is the t-test, which is a statistical test that compares the means of two samples. And it's used in hypothesis testing, specifically with a null hypothesis. That is, the difference in group means is 0, and an alternative hypothesis is that difference in group means is different than 0. So if we have an alternative hypothesis that is a 0 mean for our group, anything different from 0 means that we can reject the null hypothesis. And we do that through a t-test. We can also look at effect sizes, which tell us how meaningful the relationship between variables or the difference between groups is. And effect sizes indicate the practical significance of a research outcome. So, in other words, a large effect size means that a research finding has a practical significance. Like it means something in our society. Whereas a small effect size indicates limited practical significance. And finally, we have an ANOVA or an analysis of variance, which provides a statistical test of whether two or more population means are equal and therefore generalizes the t-test beyond two means. So, in other words, the ANOVA is used to test the differences between two or more means, and there's typically multiple independent variables and one single dependent variable that is consistent across the study. And the ANOVA is used to test the differences in each of those variables in relation to the dependent variable. So we use an ANOVA if we're looking at multiple independent variables. We also have more advanced analyses that are a little bit beyond the scope of this class, but a good example of this is what we call the MANOVA or the MANOVA, which is a multivariate analysis of variance, which is the same procedure as an ANOVA, except instead of having multiple independent variables and a single dependent variable, a MANOVA has one or more has multiple dependent variables and typically a single independent variable. So I know this is a lot of information, and the reason why I'm sort of going through it kind of fast is because in reality, for what you need to know for a licensing exam, you don't really need to know what statistical analyses need to be run. You just need to understand how they can be used in research so that you know, okay, if someone is running a significance test, they're looking at differences between variables. Someone's running a correlation, they're probably looking at the relationship between variables. So that's where we're going to wrap up our lecture on chapter 10. I will see you all in the next lecture.